Well, Neil, thank you very much indeed, and thanks to you and the organisers for the honour of being able to give this talk. As you mentioned in your introduction, I started life as a fluid mechanicist, and that's what got me into weather and climate work. So it's a real pleasure to be able to give a presentation to this meeting today. And the topic I'd really like to talk about is a sort of quiet revolution that's happened in the modelling of our weather for weather forecasts, and now more into our climate modelling, where we're really seeing we're able to compute more of the fluid mechanics than we were previously able to do. And that's really unlocking new types of forecasts and new insights into climate change. So that's sort of where I'd like to get to today. So just to orient us, and apologies, most of the audience will know most of this. How do you make a weather forecast? Well, you start by observing what the weather is doing now. And by the way, we've given Southwest horrible thunderstorms today, so that's keeping me inside and at the conference rather than yesterday, where it was extremely pleasant. So we take observations of the current state of the atmosphere and the ocean. We fuse those with a simulation model, which computes the Navier-Stokes equations, conservation of mass, conservation of energy, and the ideal gas law, for example. And then you compute that forward in time, and that's what gives you your weather model, or your weather forecast, I should say. So in a little more detail, any weather forecast starts with a global simulation. So that's what's shown on the left-hand panel here. And we tessellate, of course, the atmosphere and the ocean into grid cells. And we compute the resolved dynamics on that grid. It's a fluid mechanics conference, so you know all this. In the weather and climate world, there are always processes that are happening smaller than the grid size. And in the horrible notation of weather and climate, we call what's computed the dynamics and what's subgrid scale the physics. So apologies to purists out there, that's not my invention. So this physics are things like clouds, turbulence and mixing, the radiation, incoming radiation from the sun, outgoing radiation from the Earth's surface, which of course is a key part of climate change. So all these things need to be built into the model as additional parameterizations, if you like, in addition to the resolved dynamics. So you all know that there's a continuum of scales in the fluid mechanics, from the planetary scale right down to really as small as you want to go. If you want the smallest turbulent eddies in the boundary layer, then that's down to a few millimeters. But of course, we can't afford to compute that. So current grid spacing is, for a global simulation, something like 10 to 20 kilometers. And anything smaller than that needs to be parameterized. What we've seen over the last 25 years or so is a steady improvement, I should say, in global NWP, numerical weather prediction. So we've got time along the horizontal axis here, and a measure of the error on the vertical axis. So error going down in time is a good thing. That's how the Met Office sort of demonstrates its value, I suppose. The particular choice of error metric, of course, is very important, and this is an error metric which favors the large-scale atmospheric circulation that controls the large-scale weather patterns. So geopotential height for the experts out there. What has led to the improvement? Well, dynamical core, so the algorithm we use to solve the Navier-Stokes equation, improvements to the physical parameterization. So actually this has been my area of research in my career, and I'm delighted to say that the green line that says gravity wave drag and orographic roughness was from my PhD, actually. So I hadn't realized that was going to show up on this slide until I reviewed them earlier yesterday. So better parameterization, so better fluid mechanics and encapsulation of that in the parameterization. The blue then is higher resolution. So if we can refine those grid scales, that grid, and simulate on a smaller scale, that will improve this measure of the forecast. And then finally, observations and data assimilation in pink. So the observations are largely satellite or ground-based, and data assimilation is the mathematical method of fusing those observations with the simulation. So it's a combination of those that has led to the better forecast by this measure over the last 25 years or two. And there are lots of pub conversations amongst my community about which of the four areas is the better one at delivering forecast improvement. However, there is a different way of really changing the nature of the forecasts if we begin to resolve different types of motions in the dynamics, and that's really the theme of the presentation today. So this slide shows on the vertical axis the spatial scale of different aspects of atmospheric motion, and on the horizontal their time scale. And they start on the top right with the 100-year long climate projections. They go through into El Nino, which is a more seasonal to decadal large-scale fluctuation in the climate system. Blocking, which is what we're experiencing now with the high pressure, mid-latitude storms, the frontal situations that we're going to be getting later this week into the weekend, into the big thunderstorms, which have length scales of say 10 kilometers and time of say 12 hours or so, then down into tornadoes and turbulence and all that kind of stuff. So if I just press on, this is the kind of resolution that we're using in our current state-of-the-art weather and climate models. So that top pale brown line is where we're up to on the best climate models in the world. So the less best are at 100 kilometers. So they are just about resolving the frontal storms that are so important for the whole climate system. Our climate model at the Met Office is down to about 60, but in terms of the things it's resolving, it's well resolving those storms, but perhaps little else. If I go to the 10 kilometer, which is that middle line, that's what our global numerical weather prediction system is using as its horizontal resolution. And you can see that that's beginning to get into that picture there, which shows thunderstorms. You can see then the bottom line, which is at 1 kilometer of resolution, is really beginning to permit those thunderstorms. So the very largest scales of convective activity in the atmosphere are actively resolved as part of the fluid mechanics of the system. And so that's really the theme of my presentation here. We have, over the last 5 to 10 years, really moved through what Doug Parker at Leeds calls a sound barrier. We've moved from having to completely parameterize these convective systems to a situation where, at least on regional models, and I'll come back to what that means in just a minute, but part of the globe, we're able to at least permit the simulation of some of these larger thunderstorms or convective systems. And that changes the nature of the forecast we're able to give. It changes the nature of some of the climate change questions that we're aiming to probe. So I want to give you just a bit of an insight into that and say a little bit about some of the technical and scientific challenges that need to be overcome. So what are the scientific challenges in coarse-grained models? Well, the convection, so this is thunderstorms, any kind of cloud motion, and hence rainfall is completely parameterized. And one of the slightly awkward aspects of this is that the parameterizations actually give the rain in the wrong time of the day. So the diurnal cycle, for example, in tropical rainfall is wrong, whereas there's evidence that the convection-permitting gets it right. Perhaps even more importantly than that, there's a tendency in the parameterized convection for persistent light rain, that exciting weather of drizzle over large areas for long periods of time. So tendency for too much light, persistent drizzle, and that's missing the intense heavy rainfall. So clearly from a forecast perspective, absolutely mission critical to get those, and also increasingly important from a climate change perspective. If we can beat the resolution and get the resolution down, we begin to resolve those and we can begin to address some of those issues. And we term those convection permitting, carefully worded, not convection resolving, and perhaps that's something we can pick up in the questions later. Okay, so I think I said this already. We're squeezing down the resolution of that grid. That means we're beginning to resolve convection, although it needs lots of other things still parameterized. What do we gain there? And here's a rather old example from a case study in 2013 from Nigel Roberts of the Met Office based in the University of Reading. On the left-hand side, these are rainfall plots over the southern part of the UK. You can just see Ireland poking out on the left-hand side of the plot there. And there was a storm system that came up from the south and delivered really quite heavy rainfall, up to 45, 50 millimeters per hour, accumulated during the storm. So a big meaty storm. Left-hand side is the radar. So this is our best estimate of ground truth. And you can see, as I mentioned, that the accumulations are getting up into the red there, possibly the brown, of 50 or so millimeters accumulated. The middle panel is one of these convection permitting, running at 1.5 kilometers over a limited domain of the world, just over the UK. So it's a regional model, not global. And on the right-hand side is the older generation of models at 12 kilometers resolution, which has the convection parameterized. And I think you can see that in the parameterized convection, the rainfall is just too light. We're not getting anything like the accumulations that we observe in the radar, whereas in the convection permitting, we're doing a much stronger job there. I've got a second example which really makes the same point, but it's over India from some of our partners in the Indian Met Service. So this is showing you the coast of Africa and a rainstorm that hit there. I'm sorry, this is Chengdai. And so this is India, and middle panel is convection permitting. Bottom panel is the observations of rainfall accumulation, and you can see those very high rainfall accumulations just on the eastern coast of the continent there, which convection permitting is maybe picking up, whereas the top row with the parameterized is not. So that's the gain. We're getting those convection high rainfall events much better resolved. Now, there was an optimistic generation of scientists who hoped that if we could just buy a bigger computer, we would be able to up the resolution and we would solve this problem. So the second key message I'd like to give you is that that doesn't work. There's lots of science, and particularly fluid mechanics, that needs to be solved to get these models working. And I've managed to get a case of the dry throat, so do excuse me. So first problem is, you all know there's a spectrum of motions, and as I mentioned earlier, those go down to really the smallest turbulence motions. We are chopping that spectrum at 1 kilometer. So we are partially resolving a continuum of motions, and that's become known as the gray zone. So how do you parameterize the unresolved motions that are smaller than the grid scale in this gray zone? And that's a really major research challenge. And we've got several activities going with the academic community across the UK on that topic. And I should say, actually, at the moment, we have a mid-latitude version of this convection permitting model and a tropical version of that model, and they have different subgrid scale parameterizations. And so that's really reflecting that we haven't nailed this problem yet by any means. The second is that when small clouds are within the grid boxes, there are lots of processes that go on that describe how the droplets in the clouds grow, turn into precipitation. The updrafts associated with the thunderstorms are partially resolved, but how does that affect the droplets, that kind of thing. So that's known as microphysics, and how does that interact with the new resolved dynamics, because now you're resolving the updrafts. So the parameterization doesn't have to do that. So we had to do a lot of thinking to get the cloud microphysics scheme. The third element is that part of our weather model parameterizes the land surface, parameterizes the fluxes of heat and moisture off the surface, and they were all tuned up for persistent light drizzle. And now you've got these heavy rainfall effects. We had to get in there and do some more work on those. And then fourthly and finally, the predictability timescales of these convective storms, they have a lifetime of a few hours. So your forecast skill changes in a very interesting way. And so there are very interesting questions about how you communicate these kind of forecasts and what kind of degree of confidence you attach to them. There are also many technical challenges that I'm not really qualified to speak about, but I don't want to underplay. Running these simulations is a vast computational task, and there are some of the technical barriers that we have to overcome. Okay, so this is implemented now. So the forecast you pick up on the Met Office app and the data that goes into the BBC forecasts all use this for the, excuse me, for the UK. And here's another example of a system. And usually I play spot the ball, which one's the observations and which one's the forecast. They look similar, but of course they're different. But the point is we're getting the high rainfall event there. The forecast is the one on the left, and I know that because it's got the isobars on it, which we don't observe with radar, obviously. Okay, so we've been running with that system for a while, and I've skated over a huge number of really important technical developments that were needed. But I wanted to move on to the climate, the use of these models in climate now, which has really been the new frontier over the last 3 or 4 years. And I really have got a terribly dry throat. I do apologise. And one of the real interests in this is that the uncertainties in the changes in rainfall are very large in climate models. So I pinched this figure out of the IPCC's latest report, which was published in August of this year. You probably saw some of the press interest around that. Apologies, the quality is poor here, but essentially the message is that the changes in rainfall differ, the projections of changes in rainfall are highly different between different climate centres models. So there's something fundamental we're missing, and the argument here is that these convection-permitting models will help us along this way. So really what I'm saying is we want to get the weather into these climate models. You'll recall that many of the IPCC models are running at 100-kilometre resolution. So this is really pretty big. They're just about resolving the big mid-latitude storm systems, but they're missing all the tropical convective systems. So let's up the resolution and get some of that weather back into our climate projections. So just to set the scene a little bit here, one of the things that we do at the Met Office through the Met Office Hadley Centre is to produce the UK's climate projections. So the most recent iteration was UKCP 18 with some updates produced last year, which I'm going to describe next. And these provide the UK policy and adaptation communities with the data they need to understand heat stress, which is the top left picture, for example, in hospitals and the potential health benefits, or sorry, the health impacts of that. Rainfall and flooding, which is the top right curve, to help water companies plan for future climates, or agriculture for droughts and so on. So that there's a basic service there that the Met Office provides. So we have a very strong operational region for wanting to get these cloud permitting models into this system. So in UK, last year we added some extra data into UKCP 18, and these were simulations initially over the UK, but now if you look at the top right plot, you can see these convection permitting simulations are now running over the whole of Europe. And so what we do is we do the global simulation at roughly 60 kilometers resolution, and we embed within that, we nest within that a regional model, which is convection permitting. And then what you're seeing on the top right is a movie of that. So bottom right movie is the 25-kilometer global model in this case. So the situation you're seeing is a cold front go through with heavy rainfall along a band, just going through into France now, if we wait for it to loop again. Okay, here comes the front, the low pressure centre with the front going over Ireland, and now over the UK, so strong rainfall associated with that, and behind that cold front showers. The global model is giving widespread rainfall, as argued before, and it's maybe not getting the intensity of the rainfall in the frontal region. Whereas you can see the convection permitting is giving much more detail, as you'd expect for a finer resolution simulation. It's getting those intensities higher and more realistic. We can talk about how we evaluate these models later. I hope someone will ask me about that. From a climate perspective, this is really game-changing because now we're capturing these intense thunderstorms, and the jargon is these are mesoscale convective systems. So convecting systems that are maybe 100 kilometers across in the horizontal and persist for maybe 12 hours or so. And what we find is that the traditional message is that climate change will bring hot, dry summers, warmer, wetter winters. With this new tool, we're seeing that the summers, while on average hotter and drier, when we do get rainfall events in the summer, they're largely convectively driven and they are looking more intense. So the summer is now hotter and drier on average, but when it does rain, that rainfall will be more intense. And the plot on the left is a quantification of that, which I think I'll leave for later. So you can see we've really fundamentally changed the level of advice we can provide here. And moreover, because of the finer resolution, the resolution is fitting the catchments that we have in the UK. So not only are we getting better estimates of the rainfall, but the way that rainfall is accumulating into river flows and potential floods over the UK is also much captured in a much better way. So much more fit for purpose for both weather and climate. And I should say Lizzie Kendon at the Met Office has been leading this work along with Hayley Fowler at the University of Newcastle. Some really, really nice papers in Nature and Nature Geosciences on this work now. Similarly, we've just completed some simulations over the whole of the continent of Africa. So again, let's see, which round is it? The left-hand side now is the global model at parameterized convection. The right-hand side is nested within that global model, a convection permitting model, again with the finer detail. Here for Africa, it really suffers, the left-hand plot, from that large-scale persistent drizzle problem with the green and the blue colors. Whereas you can see that the convection permitting is organizing those storms into more organized systems that are much smaller, much more intense, and they drift off to the west, and there they initiate waves which then build into tropical cyclones. So this is an aspect of, we're not only getting better simulations and forecasts and climate projections for Africa, but there's that upscaling effect that potentially has a bigger role on the broader global climate system. So again, really nice work there, led by Kath Senior, also at the Met Office, but with lots and lots of academic input. All of this work is a very strong collaboration with the university community, particularly at universities of Leeds and Reading. Okay, I think given the time, I will probably say just a little about this. So this is one of the ways that we evaluate this convection permitting model for Africa. It's evaluated against satellite observations, these TRMM observations. Observations over Africa are notoriously difficult, and the TRIM doesn't come without health warnings. It's not a ground truth, it's a satellite derived product. And this is for frequency and intensity of rainfall. If we go into the middle plot, we see this now familiar story that the bias, so this is the error in the model, is giving too wet and too persistent. So the rainfall frequency is too persistent, it's drizzling all the time, and it's too light. Whereas if we go to the 4.5, in this case, convection permitting, we get away with a slightly coarser resolution because the convection is coarser in tropics. You can see those biases are substantially reduced, and actually I think this is a major victory. They're certainly not eradicated, and you can see over the Sahel on the intensity, we've still got some work to do there in the northern part of Africa on the bottom right plot, and indeed over the ocean, we've got some issues. But in terms of the rainfall frequency, it is much, much better in that top right diagram. Okay, so just 2 or 3 points then before I summarize. So where are we going with this? Where we'd like to get to is global convection permitting simulations. So even on weather forecast timescales, when we forecast 5 or 10 days ahead, the simulations are prohibitively expensive. So we're currently running on about 10 or 12 kilometer resolution, so convection parameterized. We would like certainly to go to convection permitting in our weather runs, and we would like to on our climate runs, which require decadal, so tens of years of simulations. And the cost there really does get enormous, enormous. So as a stepping stone to that, and an insight into some of the technical and scientific challenges we'll need to solve, we're doing this so-called K-scale proof of concept, which is a band around the equator, as per the animation in the bottom right, which is convection permitting embedded within a parameterized in the northern latitudes. And the main picture is just a zoom in on a sort of proof of concept we've done, showing the hurricanes that are produced in a simulation of this type. So that's where we're going. And just to emphasize, this is to be done to see what the technical barriers are. So, and I mean computational science technical barriers. It's to provide a data set, because we are going to have to live with parameterizations for a long time. So a data set to help give us insight into improving those parameterizations. And it will also provide us with a bit more information to help us make those subgrid models and the other aspects that remain parameterizations in the convection permitting, get those better. So when we do have the computer to go global convection permitting, we've got the science there ready to go, because it is not yet. And as I say, there was an optimistic generation in my community who thought it was just a bigger computer, but it's not. We need fluid mechanics to help us. Penultimate slide now. You may have heard the Met Office is getting a new supercomputer. In fact, we've had a really very generous investment from the UK government for a 10-year deal, which will be delivered by Microsoft. Generation 1 arrives next year, and that will be a 6 times uplift on our current capacity. And Gen 2 5 years later, which will give us an almost 20 times factor on what we've got now. This still does not get us to the point where we can do convection permitting globally, and we're looking at this kind of rate of increase to the 2030s before we do that. What it will enable us to do is much bigger regions on the convection permitting, longer climate simulation. So it will be the tool of choice for regional climate modeling, and we will be able to do experimental weather forecast runs for sure. Lots of problems still to solve there around the observations and so on and so on. So lots still to do. And then I was very keen that we had proper time for questions and discussion at the end. So let me just summarize the material that I've sort of tried to convey in this presentation. So it's really perhaps been one of the quiet revolutions in my world over the last 10 years or so to move from these parameterized broad brush models that are great for the low pressure systems, but not so great for the thunderstorms. With this new technology, we've really moved through this sound barrier. To do that, we needed a bigger computer, but we had an awful lot of computational and fluid mechanics problems that we needed to solve, and we've solved some of them. That concept is now fully implemented in regional numerical weather prediction, so the thing that provides your regional NWP. We're still working on how you measure your skill in that, because you know that convection is a turbulent flow, so getting the convective elements in the right place at the right time, it's a highly chaotic system with a forecast horizon of just a few hours. So how do we measure if we get the storm in the wrong place and at slightly the wrong time? Is that a good forecast or not? We've done, I think, a really exciting job on implementing these into regional climate projection. And in fact, UKCP18 is the first ever set of climate projections for a nation that includes these models and this new information. So we're really leading the world in this. And we're beginning to experiment, as are other centres around the world, with global modelling at this convective scale. But, and I can't emphasise this enough, there is still lots of fluid dynamics to solve. You can see that convection permitting is a generous term. We are barely resolving those overturning motions associated with the convection. So my goodness me, the subgrid scale model has got a lot to do, and the way it interacts with the moist physics. And I mentioned the land surface. But I think I'll pause there, Neil, and look forward to questions.